Let's say a major storm washes out a key bridge in your supply chain. You need to reroute trucks and you need to do it fast. You're faced with a choice. Do we build a temporary connector or do we double down and boost capacity on a secondary corridor? That's the exact kind of scenario we're tackling in this orientation for Case Study 09, Routing and Optimization. Over the next few hours, you're going to focus entirely on building your predict skill for engineered systems. We've already covered how to identify network structure, measure criticality, and infer patterns. Now we're shifting from just observing the system to actively changing it. We're going to look at routing, flow, and optimization, and we'll do it by answering one of the most common and statistically treacherous questions an engineer can face. Here's the scenario you'll be working with. Imagine you're an analyst for the Lakeside Department of Transportation, and you're evaluating their current bike share network. You know there are weaknesses in the system. Some stations are barely connected, and certain corridors get completely overloaded during the morning commute. So a planner pitches a fix. Maybe they want to add a brand new station, build a direct connector between two distant hubs, or just boost the capacity of an existing corridor. Before millions of dollars are committed to pouring concrete and installing hardware, you as the engineer have to ask this crucial question. If we add a station, build a connector, or boost a corridor, does this intervention actually help? Or is the change in ridership just statistical noise?
This brings us to a really important contrast: the naive approach versus the network-aware approach. The naive alternative, which honestly most engineers naturally reach for first, is relying on a single point estimate. You look at a spreadsheet of observed ridership, calculate the current average path length, apply the new edge, and recalculate. Simple, right? Well, the problem is that ridership data is incredibly noisy. A pair of stations that saw 47 trips last quarter might see 30 or maybe 65 next quarter, purely by chance. So relying on a point estimate from one snapshot of noisy data is essentially lying to yourself. Instead, we're going to use the network-aware approach. We'll run a counterfactual Monte Carlo simulation to find true statistical confidence. We're going to simulate hundreds of parallel realities to see if our proposed change actually survives that noise. But before you even touch the interactive tool, I want you to grab your physical sketchpad. Remember, the real thinking in this course happens on paper. The software is just there to verify your logic. In this case study, you'll be looking at a map of the 15-station Lakeside network. By eye, I want you to work through these 3 steps by hand. First, draw the proposed treatment on the map. Let's say a new direct edge. Second, mark the specific nodes you believe will benefit the most from this new routing. And third, write down your prediction for how the average path length will change. Is it going to drop massively, barely at all? Commit to a prediction on paper right now. As you draw this out on your paper, take your time rendering the network. Draw the nodes as nice, clear circles and the edges as slightly curved lines. And here's a critical tip for this specific system. Grab a mustard yellow marker and highlight the bridge stations. You'll quickly notice that the busiest stations, the high-degree hubs, aren't always the most structurally critical. Bridge stations might look sparse in traffic, but they are the sole connectors between distinct clusters of the city. If your proposed intervention ignores these bridge stations, you could inadvertently leave the whole network highly fragmented, so keep a close eye on them. Once your sketch is done and your prediction is locked in, then you can open the interactive Lakeside Monte Carlo simulator. This browser-based tool lets you verify that hand-drawn hypothesis you just made. The workflow is pretty straightforward, but it's rigorous. First, you'll set up your baseline network using the observed, noisy data. Second, you apply your intervention, like adding that new edge you just sketched. Third, you hit Run to execute the Monte Carlo simulation. And finally, the tool calculates the difference, comparing the intervention metric minus the baseline metric. To really understand what that simulator is doing when you click Run, we need to talk about Poisson resampling. This is the statistical engine running under the hood. You see, we don't just calculate the metric once. The simulator redraws every single edge's weight from a Poisson distribution, where the expected value, lambda, is simply your originally observed weight. It does this over and over again, say 500 times. What this does is generate a distribution of plausible network realities that are entirely consistent with the actual trips we observed. We're essentially asking, given the natural randomness of human mobility, what are all the realistic states this network could be at? You'll be using the simulator's dashboard to configure these runs. You can select different treatments, like testing out a new station versus boosting an existing corridor. You can also swap out the metric you care about. Maybe you're looking at average path length, or maybe you really care about the worst served node. You can adjust the number of simulations too, running 100, 500, or 1,000 iterations. By applying your intervention to each of these hundreds of resampled networks, you build a 95% confidence interval. That tells you exactly where the true effect of your engineering intervention is likely to land, regardless of the underlying noise. While you're exploring the dashboard, you're going to encounter one of the core learning checks for this module. You'll run the simulation tracking average path length, and then you'll run it again tracking the worst served node distance. You'll immediately notice that the histogram spread for the worst served node is much, much wider than the average. Now, I'll let you figure out the underlying engineering reality of why maximums are so much more volatile than averages, and why equity-focused metrics inherently demand more data to achieve statistical confidence. It's a crucial lesson in system design, but you'll figure that out yourself. After you've built up your intuition in the interactive lab, you'll move over to the coding exercise. Open up the code folder in the course repository. Inside the 09_counterfactual directory, you'll see how this exact same resampling analysis is executed in plain code. Whether you prefer the example.r script using tidyverse and iGraph, or the example.py script using pandas and networkx, the structure is totally identical. You'll see exactly how to write the loop to permute the edge weights, apply the structural change, and aggregate the results. This is the exact code you're going to adapt when you run this counterfactual analysis on your own datasets for the final project. Before you begin, there is one major conceptual misconception that this case study is designed to dismantle entirely. When you run your Monte Carlo simulation and look at the final confidence interval comparing your baseline to your intervention, that interval might cross 0. A lot of analysts look at a CI containing 0 and immediately conclude, well, the intervention didn't work. That is completely false. A confidence interval that crosses 0 is a statement about your lack of evidence, not proof of a failed intervention. It simply means the signal of your improvement wasn't strong enough to rise above the noise of the system at your current sample size. Please keep this fundamental concept in mind when analyzing your final output. To wrap up this orientation, I want you to leave this final prompt on your screen. Grab your pen and sketch this out right now before you even open the case study page. I want you to draw a transit network with at least 3 distinct, disconnected components. Pick one edge you could add to connect them. Predict how much the average path length will change. Okay, now, pick the wrong edge. Pick an edge that looks like a logical addition, but actually does very little to improve overall network efficiency. Draw it out, write down your reasoning, and then dive into case study 09. Remember, the syncing happens on the paper,